let me first point out that the slides, the PDF file of this presentation, but also of the exercises, can be found at that website, and you can download the PDF file of these exercises also from there. I hope that the fonts of some equations are visible or not. I don't know, on my PC they are, but that seems to depend a little bit on the type of Windows or of the version of Windows, whether you see all the equations properly or not. Okay, we started the discussion about this Schrödinger-like equation. Actually, since we are doing Kohn-Sham theory, one would call this the Kohn-Sham equation for solids. And we had started the discussion what we have to consider, how we represent the solid, which kind of basis functions we want to use in the expansion of these wave functions, how we can treat exchange and correlation effects, DFT, LDA, GGA, beyond GGA or so, and we stopped in the description of relativistic treatment and also treatment of spin, non-spin polarized. That means when all spins, spin up and spin down electrons, are equally occupied, have the same wave functions. We don't care then in such a case about spin. We just do what is called non-spin polarized calculation. If we have a certain magnetic moment, a certain magnetic order in our case, then we have to do a spin polarized calculation. And for such magnetic cases, and if we then treat also relativity, then in a more advanced version, then there is a certain coupling, and we will continue now on that topic. Just to sum up what we heard about the relativistic effects, there are basically four main effects. The first one was the mass velocity correction. That is the obvious thing you would say about relativity. What means relativity? It is important when particles move very, very fast, approaching the speed of light, and that happens for heavy elements and deep core states. So what was the correction of this term? Which electrons did it affect most? Who remember that? The core electrons of heavy elements. Let's say the 1s or electron of gold or so was circling around so fast that this is the major effect. The second point we called was the Darwin S shift. And I explained to you, this is not a real classical analogon, but it can be explained by what is called the Zitterbewegung. It was analyzed already by Erwin Schrödinger a long, long time ago, that it comes from this interference of positive and negative energy states and so on. So it's a little bit more complicated term. The effect is also clear. It is also often called the Darwin S shift. So it affects the S electrons in particular in the same way as the mass velocity term. So it will contract these states. The third term, which is often called the relativistic effect, but I would say often in many cases these effects are even more important than this one, is what we call the spin-orbit coupling. That simply is the interaction of the spin magnetic moment, denoted by S, of these electrons, with the magnetic field, which is produced by its orbital motion. So you know, if a charge is moving around, it's processing, it produces a current, and that produces a magnetic field, and this can interact with the spin. And this coupling between angular momentum L and spin S needs to be considered, and this is the spin-orbit coupling. And there is a fourth very important in many cases, or sometimes it's even, you could say, the most important effect. They are indirect relativistic effects. We talked about the large change of the 6s wave function of gold. Now, the 6s wave function is a valence wave function, and this electron is certainly not really relativistically moving around, but it had a strong, strong influence, and that was the orthogonality constraint, because these outer electrons have to be orthogonal to the inner shells. And there is a second effect, and that was that these outer electrons, let's say a 3d electron or a 4f electron with a higher L quantum number, they see a modified electrostatic potential, because the core electrons, 1s, 2s, the 2p or so, they are contracted and they shield the nucleus better. So again, a very indirect effect. These electrons are not necessarily really the relativistic in that sense, but the indirect effect affects them very, very much. Now let's go one step further and let's see what happens if magnetism and spin orbit comes together. So the first important thing is spin orbit coupling couples the magnetic moment to the lattice. So if we do regular spin polarized calculation, let's say BCC iron, we can do a calculation, we get out a spin magnetic moment of 2.2 μ, and we say it's upspin. And sometimes we even draw an arrow somewhere on this atom, but this drawing of this arrow does not mean that the magnetic moment really points, let's say, in the z direction. This is absolutely not defined if you don't take spin-orbit coupling into account. It just means that there is more spin-up electrons than spin-down, so you have a spin magnetic moment in iron. A better way would not be to call it spin-up, because this always means an arrow in this direction, but let's say you have alpha or beta spin, or majority or minority spin. These are all the same words. Sloppy as one is, usually one calls this the spin-up magnetic moment, or the spin-up electrons. And however, magnetism, there could be also a second source of magnetism, and that is the orbital magnetic moment coming from the orbital character, the L character. And with spin orbit, there is now a coupling between this orbital magnetic moment and the spin magnetic moment. Now, an orbital moment means definition of an LZ, for instance. And now this LZ can be connected with your lattice. Only when you have this connection, then you can say, my magnetic moment may look in the Z direction, or in the 1-1-1 direction, or in some other crystalline direction. So only with spin orbit, the total magnetic moment has a defined direction with respect to the lattice. So just in this example, you have here an orthorhombic lattice with A, B, C, different length. And if this would be magnetic, this arrow here now could mean that the magnetic moment really points along the Z direction, or in this case, along the A direction. And that would give you a different situation in principle. Now, the problem of such calculations, or when you want to calculate this, you don't know a priori in which direction the magnetic moment wants to look. So you have to do the calculation in such a way that you define as an input in which direction you want to let your moment look. So you define one calculation. Let's make the moment along the z direction. You do your self-consistent calculation, including spin-orbit coupling, you get out the total energy. And then you do the second calculation, let the moment point in this direction, and such calculations as function of the direction allows you now to calculate things like what is called the easy or the hard axis of magnetization. That means in which direction really does the spontaneous magnetic moment want to look, and what energy, that's the magnetocrystalline anisotropy, does it cost? How much energy or which external magnetic field do I have to apply to flip the moment from this direction to another direction? Okay? So this is done in such ways, and the consequences of this is that spin-orbit coupling in magnetic systems also reduces the symmetry eventually. Because the symmetry operations act now not only in real space, but also in spin space or magnetic space. And the magnetism does not behave in terms of symmetry like an arrow plotted like this, but it behaves like a pseudo-vector. What is a pseudo-vector? It is this circle indicated here. That is because it's not the magnetic moment which is important for the symmetry, because the magnetic moment is the outcome. What produces the magnetic moment is this current. And this current loop, therefore, is what you have to consider when you want to know about the symmetry property of a certain magnetic case. So you have to consider the symmetry of this current loop, whether it's in this direction or other, or if a symmetry operation would flip it or whatever, and not about this magnetization arrow. Okay? Consequences are it could be that the number of symmetry operations is really changing. The most simple and obvious example is a cubic crystal. Take cubic BCC iron. How many symmetry operations do we have in this space group? What's the maximum you can have? 48 symmetry operations, right. It's cubic symmetry. 48 rotations and reflections and inversions, and so that's the maximum. Now, if I have now spin-orbit coupling switched on, and iron is magnetic, I have a situation where I have a current loop, or if you want, a magnetization in a certain direction. And then the z direction, for instance, is of course different from the x and y direction. That means cubic BCC iron, magnetically ordered, ferromagnetically ordered, including spin-orbit coupling, is no longer cubic. It reduces to tetragonal symmetry. In difficult cases, it can even happen that atoms become non-equivalent. The problem is that when you have magnetism, time reversal symmetry is not a symmetry operation a priori anymore. You heard that also in the previous talk and in the WIEN2k talk from David. And that means we can a priori not add inversion for our K-mesh. In other words, the energy, the eigenvalue at the K point K or at the K point minus K might be different. Usually, always without spin orbit coupling, an eigenvalue of plus K or minus K is the same. We don't need to calculate both of them, just do one. The other one must be given by symmetry. As soon as you have magnetism and spin orbit coupling, this is not necessarily the case anymore. Yes? I didn't hear the
you said you consider the current loop instead of the magnetization. So does it mean you're considering the orbital contribution or something?
No. I'm not cancelling the orbital contribution.
Considering, I mean. Considering, yeah.
Yes, exactly. Yeah, sure.
But the spin and orbital are
the
coupled?
spin is then coupled with plus or minus to the orbital magnetic moment. So the spin aligns then basically more or less automatically in the calculation, but collinear in that sense to the orbital moment. Okay, so the important thing is the orbital magnetic moment. That is what defines you really the direction in space. Okay, exactly. I have an example about the symmetry right here, which I will explain. Just from the practical point of view, in WIEN2k there is an initialization routine for spin orbit, init SO, which should be executed, and that will detect the symmetry settings automatically for you. So you don't have to care. It even writes, in the worst case, a new struct file with splitted atomic positions and the proper symmetry. Once you have provided in the input file in which direction do you want to put your magnetization. Now, let's see this example. This is this lattice here, which we already showed before. It has 4 symmetry operations. Okay? Identity, a mirror plane normal to the x direction. So x is A. This is this mirror plane here, shown here. A mirror normal to y. That's the other mirror over here. And then a twofold rotation axis along the z direction. This is indicated by this arrow over here. Okay? So we have these 4 symmetry operations without spin-orbit coupling. Now let's take the direction of magnetization in the 1, 1, 0 direction as it's printed or indicated in this picture. That means if my magnetization looks in this direction, in the x direction, I will have a current loop as indicated here. And of course, the identity preserves this. There is no change. We call this a symmetry operation type A. The mirror plane mx, this is this mirror plane here, that preserves, of course, the current loop. It would not preserve this arrow, right? But the current loop is not changed by that. That means this is also a symmetry operation. While this mirror plane, as well as the twofold rotation axis, will flip the current loop. So it's not a simple symmetry operation for this current loop. Only together with time inversion symmetry, it is still a valid symmetry operation, so we can use it. But in the code, in addition to this, we have to add the inversion operation to that operation to make it, again, automatically a symmetry operation. So with this direction, all 4 symmetry operations are preserved. Also, for the latter 2, we have to do a special manipulation in the lattice. If we now would put the magnetization along the 1, 1, 0 direction, so in the diagonal here, right? Then identity is no problem. Also, the twofold rotation is no problem because with inversion, with rotation and inverting, we would again keep this, but the other 2 symmetry operations would be gone. So this would be a case where I would have lower symmetry because I put my magnetization in a special direction. And of course, if I would use an odd direction in somewhere in space, then probably I would lose all the symmetry except the identity. If we want to treat now this, we have to solve what we call a Pauli Hamiltonian for a magnetic system. That means our Schrödinger equation, Schrödinger-like equation, is now actually a 2x2 matrix in spin space because we have this Pauli spin operators, the sigmas here and here. These are 2 by 2 matrices. So our Hamiltonian is our well-known kinetic energy. And remember, usually this is changed. It's not the rest mass of the electron, but it's this enhanced mass. We have an effective potential where we have the external potential, the Hartree potential, the exchange correlation potential, was also discussed before. And then we have an effective magnetic field. This B effective could be an external potential if you apply a magnetic field, but even if this is 0, if you have spontaneous magnetic moments, you have an internal magnetic field. This comes from the exchange correlation field. This field is proportional to the magnetization density. Remember yesterday the talk, we could speak of spin up and spin down density, or we could add it and make a total density and form the difference of spin up minus spin down densities. That is what we would call the magnetization density, and we have to take the derivative of our exchange correlation functional with respect to the magnetic moment, and this gives us the exchange correlation field. It's like an effective potential, but it is spin dependent. And last but not least, we have the spin-orbit coupling term here, where, as I said, it's coupling the spin and the angular momentum, and it is proportional to this dV over dr, so it's very important inside the sphere. If I expand this equation, okay, it looks like this. So we have a spin-up line and a spin-down line, basically. You have here our Hamiltonian. In the diagonal term, the direction of the exchange field in Z is different here or here, plus and minus. Okay? And we have also off-diagonal term. This exchange field is a vector field. It's not just up and down, a scalar field, but it is now a vector field. Okay? And that could, of course, be on every atom in our unit cell differently, pointing in different directions. So Bz and Bx, By means you could have different Bx, Bz, By on different atoms in our unit cell. So in such a formulation, we could describe non-collinear magnetism. What means non-collinear magnetism? It means that the magnetic moments from one atom to the other may have an arbitrary angle in between. Okay? As you can see it here, this is maybe some spiral, but it's not necessarily that it is spiral. It can be some canting only, or all kinds of things. This Hamiltonian acts on our wave function. This wave function, therefore, must be a non-pure spinor. That means the wave function must have at least two components. Actually, it has four components because each of them has a large and a small component. Remember that from yesterday. But for simplicity, I'm writing here only the large components. And psi1 and psi2 are mixed together to a total psi. We have non-pure spinors, and we can have a non-collinear magnetic moment in our material. Now, let's simplify it. That was the most difficult, most general, most difficult case. Let's simplify it to see how we can, at the end, come to a standard magnetic solution or even to a non-magnetic solution. The first simplification would be, let's drop the spin-orbit term. What does it mean? Our exchange field suddenly is a scalar, if you want. We have only one number, Bz. X and Y is not defined anymore. We take Z as the maximum. That's it. The magnitude. And it's plus and minus over here. This is off-diagonal terms are 0. And therefore, this system can be block diagonalized. It separates into two independent equations, right? One for spin up and another one for spin down. And therefore, the resulting wave functions are pure spinors. The wave function for spin up is pure up. Spin down component is 0. And the other way is like this. Of course, the eigenvalues of spin up are not the same as the eigenvalues for spin down. But an up eigenvalue has only an up contribution here. Okay? That is what we would call a standard spin polarized calculation. And remember, if I draw now arrows here, it does not mean that this arrow really points in up and down direction. It could also be that all the arrows are in a certain other direction. All it means that if I assume one vector is going, let's say, in this direction, then the others will have the same direction or 180-degree opposite if it's an antiferromagnetic or ferrimagnetic arrangement. But, yeah?
And if I say that the solutions are, spinor solutions now, can we, so we are thinking that exchange correlation field also is in Z direction, purely.
Yeah.
Can that be seen easily? I mean, because it's a current-induced field.
The orbital moment without spin-orbit coupling and without external field is 0. There is no driving force which occupies an m+2 or -2 state differently. Only when I have spin-orbit coupling, then something what usually in atomic physics might be called Hans rule or things like this can be applied. And then you get a different occupation of +m and -m. Okay, and that gives you a certain orbital moment, and that gives you then a certain direction in magnetic moment. Yeah. Other questions? Okay, so just remember, this drawing does not mean that this is a real lattice, that this vector points in this lattice perpendicular to this chain. It just means alpha spin and beta spin. And on these two atoms, they would be the same size, only different, alpha and beta, or majority and minority. And on this atom, the magnitude of this magnetization, if the spin up occupation and the spin down occupation is the same, well, then this term is, of course, also 0. And that means that this Hamiltonian gets the same as this one. So we can forget about this line, because it's enough if we have this solution. We know then this solution is they are the same. And the eigenvalues for spin up and spin down are the same. And that is the standard non-spin polarized or non-magnetic calculation, which we do whenever we know that our system will be non-spin polarized, non-magnetic, because it simply saves a lot of computer time. Okay. In WIEN2k, you would consider these as spin polarized calculations. There are extra scripts which concerns or which directs the calculation to do it spin polarized, so for spin up and spin down different. There are often some complicated situations where unconstrained magnetic calculation may have difficulties to converge. So think of a situation where the total energy as function of the magnetic moment could look, for instance, something like this. Oops. And then it's going up. So in such a case, it means that the total energy almost does not change whether I have a non-magnetic solution or a certain magnetic solution. And in particular, it also means that the result may depend on our start. If we start our SCF cycle with a magnetic moment sitting here, it probably will converge very slowly, but maybe it will converge to this way, to this energy and this non-magnetic solution. If we start here or here or here, then we will get this solution. So this is something which is not very favorable. It also takes many SCF cycles because usually such a situation is converging very, very slowly. And then we can do something which is called a fixed spin moment calculation, FSM. And that means in an input, we define the magnetic moment to be 2. Okay? And then we do the calculations for a magnetic moment of 2. Can somebody guess what that means? Yeah.
You get around this problem always by starting with the saturation moment. I mean, you push it up and then you'll always, if it's there, not there, but
what is if the situation looks like this? It will converge to this way, to this energy and this non-magnetic solution. If we start here or here or here, then we will get this solution. So this is something which is not very favorable. It also takes many SCF cycles because usually such a situation is converging very, very slowly. And then we can do something which is called a fixed spin moment calculation, FSM. And that means in an input, we define the magnetic moment to be 2. Okay? And then we do the calculations for a magnetic moment of 2. Can somebody guess what that means? Yeah.
You get around this problem always by starting with the saturation moment. I mean, you push it up and then you'll always, if it's there, not there, but
what is if the situation looks like this?
Yeah, but that's like.
Then I'm ending up here.
Yeah, I understand.
Okay? Then I have bad luck. I don't get my ground state either. That's possible, of course, yes. I can, of course, also do a calculation where spin orbit is then present, but this is not present. Yes. Okay. I would not call it perturbatively, because perturbation theory doesn't apply, the variational principle doesn't apply. So if you do a perturbation theory calculation, you get out an energy, but you don't know if it's higher things. This is still variational, okay? So it's a variational calculation, of course, with a restricted basis set, and yeah. But it's still variational. Yes, we can do this. That means still that we have then 2 times the number of eigenvalues, spin up and spin down eigenvalues together in one calculation. Basically, we get twice the number of eigenvalues, because we couple this now. And depending on symmetry or not, without inversion symmetry, it can give you a splitting of the bands. So a typical case is in semiconductors, in gallium arsenide or so, you have at the top of the valence band a 3-dimensional degenerate state without spin orbit coupling. Gallium arsenide doesn't have inversion symmetry, has heavier elements, gallium and arsenic. So if you put spin orbit coupling, it will split these 3-dimensional degenerate bands into 2 and 1 and give you this effect. Okay? Sure. Other questions? Okay, so my question was, if I want to do this FSM calculation, so I want to define the magnetic moment and fix it, what do I have to give up then? What we usually have. If we do a spin polarized calculation, we have spin up electrons and spin down electrons. How do we fill these states? Until we get the total number of electrons into my systems. So that means n up plus n down must be the total number of my electrons in my system, obviously. How do I get my magnetic moment? The difference, n up minus n down. Okay, that gives you my magnetic moment. Fine. Now I'm fixing my magnetic moment. That means I'm saying this should be 2. Of course, this must still also be obeyed. It's also clear. So I'm with these two equations, I have 2 unknown. I can solve the problem. Okay? But how do I get this n up and n down, or what is not fulfilled, which is usually fulfilled? I do not have a common Fermi energy anymore. Because think of a density of states, okay, spin up, spin down, shifted, and usually you fill up your states up to a common Fermi energy until the integral of this density of states is this, and the difference between these integrals is my m. Now I'm forcing m to be something. That I can only do if I say, I have to use this Fermi energy for this state, and maybe this Fermi energy for the spin-down electrons. So I have to introduce 2 Fermi energies. What's that? Is there any physics behind that? How can I interpret that? What could shift me, give me this energy shift? An external magnetic field. So I'm fixing the moment, and then I can interpret this delta EF as my external magnetic field, which would give me a magnetic moment of 2. Okay? It's much easier than really applying a magnetic field to a solid, because this is a very difficult thing. What happens with a magnetic field and periodicity in a solid? An external magnetic field breaks the periodicity. I don't have a unit cell which is the same everywhere. The field will be different in every unit cell, of course. If I have somewhere an origin of a field, it's not a constant anymore. I have no periodic boundary conditions anymore with a external magnetic field. It would be a disaster. Okay? But with this trick, I can do, so to say, the reverse engineering. I can look what would be the field for a certain magnetic moment. And I can do this calculation now for a couple of points and map out this energy curve and find that there is this meta-magnetic transition probably. Things like this can happen, for instance, if you apply now pressure or temperature, means expand that. These things can shift easily a little bit, making this different. And that is the origin of the so-called INVAR effect in a magnetic material. What is an INVAR effect? INVAR, an INVAR alloy, invariant with temperature. You know, normal materials, metals in particular, have a change in their volume with temperature. There's a thermal expansion. And if you do this on the Eiffel Tower changes its height, I think, by 30 or 40 centimeters from midnight to 12 o'clock noon or something like this, whatever the temperature difference is. So it really changes its height. And people have really put a material, for instance, a nickel iron alloy in the right concentration, put a wire on that, and this alloy has no thermal expansion. And with this alloy, with this wire connected at the top of the Eiffel Tower, they measured with some device how much the change of the Eiffel Tower with temperature was. Okay? You had the Eiffel Tower, normal steel, which changes its length with temperature. The iron-nickel alloy stays constant with temperature, and then you see the difference between these two lengths. And this can be explained with such a transition that with changing volume, it would change the magnetic state from non-magnetic to magnetic, and that would have a slightly different volume. And that compensates the thermal expansion and shrinks it again. So things like this, for this run FSM is very useful. Eventually, one could also do antiferromagnetic constraints or things like this. As I said, we add then spin orbit in the second variational step. And just for a technical command, if you ever do calculations with WIEN, never mix a spin polarized and a non-spin polarized case calculation in the same directory. That will give you a mess.
So in the second method, is it we are scanning the whole M region and seeing which is the...
Exactly. Yeah? So you do, as in input, you say 0, 0.5, 1, 1.52, and you do 10 calculations. But
the range would be fixed by...
that's up to you. I mean, this...
What ensures that that doesn't fall down?
Nothing ensures this except, let's say, intuition or physics or whatever you call it. You know there is a saturation magnetic moment, right? Even in a strong external field, you can get only a certain magnetic moment. That basically depends on the number of valence electrons you have. I don't know, think of a certain material. What is the maximum moment you can get? If you have titanium, yeah, maybe you have 4 valence electrons, so you can hardly get a larger spin moment than 4. Or, I mean, you will not polarize your core electrons, and that moment, that magnetic field doesn't exist. I mean, which would polarize the core electrons. Yeah? So this is giving you the maximum value. You also see it in the total energy. The curve is really, as I plotted it, it goes up to whatever. Because once I have shifted that so that all states here are empty and all are occupied here, every larger magnetic moment means I have to shift these core states up here that they get unoccupied. So this gives me a huge energy.
What happens if there are multiple magnetic sites? Means iron, cobalt. Then how do I fix the only saturation magnetic moment and I will get the correct magnetic moment at each site?
I can only fix the total moment.
Then what about means if it is 8 mu b, then I can get from 4 4 also from 6 2. If there are 2 sites, then will I get the correct ground state for each?
Well, again, there's never a guarantee that you reach the correct ground state, but it is very likely. Okay? So typically, we do not find problems, let's say, in this picture, that when you have, this would give you a certain net magnetic moment, okay? But it is usually fine and not a problem, okay? Such a situation has only one competition typically, and that would be a non-magnetic calculation, or a different spin order. That means all spins, for instance, ferromagnetic, okay? Or this spin may be also flipped or something like this. So if you have this you have to test in the extra separately by a different input. We will do an antiferromagnetic calculation during the exercises where we have as an input already to specify that one vanadium atom should be spin up and the other vanadium atom should be spin down. Then we do the calculation, and if this antiferromagnetic alignment stays constant, then this is at least a metastable solution. Okay? Then we would do another calculation with both vanadiums spin up and compare the total energies between these two and see what is the better energy, that is the lower state. And then we could do a third calculation, make the calculation non-magnetic, and compare this third calculation, the third total energy, with the two previous ones. And that gives us, in this search of collinear magnetic structures, the lowest energy. Oops. Okay. Of course, in principle, it is also possible to treat this more complicated state, this non-collinear magnetic state, however, not in standard WIEN2k, but we have called this an extra program. It's called WIEN-NCM for non-collinear magnetism. It is a clone of WIEN2k, and it can be obtained from every registered WIEN user on request. It allows you really, it uses spin-orbit coupling already in the first variational step. It's therefore a fairly expensive method, but allows you also to treat spin spirals and all these kind of things. So you can get a description, or can describe such materials. Where is non-collinear magnetism interesting? What do you think? In which materials is this important, more important, let's say? Frustrated systems, right? So, you know, you have heard about antiferromagnetism, right? So it's clear if I have a lattice, two atoms, then it's not a problem to have spin up and spin down here. Okay? If they want to have it, they want to have it. Now we could have four atoms, a square lattice. Well, there is certain possibilities how I can arrange my lattice. I can make all neighbors of this atom antiferromagnetic. Okay, for instance. And they are all happy because this one will then be surrounded only by spin up. So this is still a possibility, not a problem. But what happens if I have what is called a triangular lattice? If this is spin up, okay, and it wants to be antiferromagnetic, good. Let's make this spin down. But what should I put here? Spin up or spin down? This is unhappy. It's not a good solution. So this is a favorable case, if it wants to be magnetic, that it makes a non-collinear solution where the moments might put like this, might be placed like this, pointing in the center, and they have an angle of 120 degrees, which is with each other. Okay. In the input file, just for curiosity, you have to define this direction of magnetization, 001 direction, for instance, here. You could define here these relativistic local orbitals, which I mentioned yesterday, because we don't have this p1/2 basis. It's only interesting for elements which have p states in a semicore region. That means at low energy, minus 10 electron volts or so, where this p1/2 and p3/2 splitting is very important and present. And a computational trick, if you want, it allows you in this line to switch off spin-orbit coupling for certain atoms. Why would you do this? Obviously, if you have an, I don't know, strontium iridium oxide, where is spin-orbit coupling important? For which atom? For the iridium, obviously. Now, WIEN has a restriction. The calculation of atomic forces, which I come in a moment, is not implemented together with spin orbit. That means when you have spin orbit on all the atoms, you cannot do structure optimization. So switching off spin orbit for oxygen and maybe also for strontium allows to optimize the position of oxygens, and basically there is no approximation because the relativistic effects on the oxygen atoms will be, the spin orbit effects on oxygen atoms will be more or less zero, and on the iridium they are fully taken into account. Okay, so that was the main goal, and let me now give a summary of all these considerations. We want to solve this Kohn-Sham or Schrödinger-like equation in a solid. The wave function cannot be found analytically like in the hydrogen atom or so, no way. In principle, one could try everything numerically on a grid or so, but this is very, people are trying it now, but it's not an easy task. Why is a numerical solution so difficult? What do you think? Numerical means you make a grid, right, and describe the wave function point per point on your grid. What is the problem? One of the problems, let's say. It's the different localization or variation of wave functions for different kinds of electrons. For valence electrons, you need a dense mesh in the bonding region. But still, a valence wave function may have several nodes. If it's a uranium 6s function or whatever, it has many nodes, and these nodes are tiny little together. So you have to have a very, 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 very dense mesh all over the place to describe this properly. Unless you are using pseudopotentials, then maybe you have some chances. But it's problematic. So therefore, most methods use an ansatz of a linear combination of some basis function. So we expand our wave function in such a scheme as a linear combination of some basis functions, and different methods use different basis sets. That could be LCRO methods, where you have Gaussian functions here. That could be pseudopotential methods, which use here only plane waves, or what I have stressed, we use these augmented plane waves for these phis here. Okay? That is different in different method. The rest is the same, basically. What are you using then? You're trying to find the best wave function and the lowest energy by the variational principle, written like this, and also discussed yesterday a lot in these lectures. And this leads to what is called either the secular equations. If you do this in quantum chemistry for the H2 molecule, you can do this by hand with some approximate Hamiltonian and solve this on a piece of paper easily. Or if your number of basis functions k is very large, then you get a set of linear equation, which is called in mathematics a generalized eigenvalue problem. So these H and S are the Hamiltonian and the overlap matrix. So this is a matrix. If I do this derivative here, this becomes a matrix. The C is the matrix of my eigenvectors. These are these coefficients for each state n. And the E is a diagonal matrix containing the eigenvalues. In our methods, we use a basis function, this dual basis set. These LAPWs or APWs, they depend on a G vector. I've written it now with a G instead of a capital K. And this basis set is different in different regions of space. In the interstitial, it's plane waves. Inside the spheres, it's this expansion in angular momentum, while m, times the radial function at a fixed energy, and the u dot if I'm using LAPW, right? And then we have another basis set, a second basis set. These are these local orbitals. They look very much similar like this, but They are not connected to any G, not to the plane waves, but these coefficients have their own coefficient C in front of this basis set. So then I form a linear combination of those basis functions. Typically, I need about 50 to 100 of these APWs per atom. That means my matrix size, which I have to solve here, if I have 100 atoms in the unit cell, is approximately 5,000 times 5,000 or 10,000 times 10,000. If I have 1,000 atoms, I might reach matrix sizes of 100,000 times 100,000. That you cannot store on a single computer anymore, but we can, using MPI, we can split this matrix into blocks and distribute this on different cores. On a large compute cluster, we can do such calculations also. So the matrix has three parts. There is a plane wave part that comes from this basis set. So if we, let's say, have just one atom, this will be 100 plane waves, 100 by 100. And if you have just one atom, let's say for simplicity sodium, we will have S and P local orbitals, 4 local orbitals, because we have one sodium in the unit cell. So this block will be 4, and there will be matrix elements between the plane waves, between the local orbitals and the plane waves, and between local orbitals and local orbitals. And that gives you this 104 times 104 big matrix, which we have to diagonalize on the computer, get the eigenvalues and eigenvectors, and n here denotes the band index. And this procedure we have to repeat for many, many k points. Look at this k index here, because this enters here everywhere in the Brillouin zone. So for the gamma point, delta point, x point, or k points. And at the end, we have to do this integration over the Brillouin zone and find a new electron density. This gives me a new potential, and this leads to this SCF cycle, which was stressed in a couple of talks before. So the actual calculations are usually really loops within loops, many loops within many loops, if you really want to do a calculation from full first principle without any knowledge. You would start with some structure, A, B, C, alpha, beta, gamma, atomic positions denoted as R alpha, either from experiment or from your imagination. Okay? With this, you start your SCF cycle. In the SCF cycle, you have this loop over many k points in the Brillouin zone. Using the variational principle, you find for every k point the eigenvalues and wave functions. You get the valence charge density as sum over all these wave functions at every k point. And with this new density, you get a new effective potential. It will be different at your starting potential, and you iterate your SCF cycle until you are done. And then you get out basically, let's say, one number, namely the total energy, and eventually the forces acting on all the different atoms. And you can move your atoms according to the forces in different positions and do a structure optimization to have this outer loop here. Okay? Total energy calculation is obvious. We have 3 contributions, and Coulomb energy, the interaction of the electronic charge density with the electrostatic potential of the nuclei with the electrostatic potential, the kinetic energy contribution written as the sum of eigenvalues minus the integral of the density times the effective potential. Is that clear how such an expression comes, where this comes from? Schrödinger equation, H psi equals E psi. So on there you have this E, but this E contains not only the kinetic energy, obviously, but also the potential energy, and that I have to subtract. Okay? And then we have the exchange correlation energy, which is an integral of this exchange correlation energy density times the electron density written like this. This gives me the total energy, one single number after all these horrible many loops over loops. And this one number tells you nothing. It will be a wrong number. The true total energy will be completely different because our approximation for exchange correlation is so bad that the hydrogen atom does not come out as 13.6 eV or so. So very bad. But it will be one number. And the use of this number is only then if you compare it with another calculation. You change your lattice parameter, you change your crystal structure, and compare total energies with this. And this difference, we believe, the total value of this number is a not complete, but is fairly wrong, so to say. Okay? I was talking about forces, which are very important for structure optimization. An atomic force is clear, is the negative derivative of the energy with respect to the position of this atom. Just think of such picture, total energy as function of, let's say, the distance between two atoms in a two-atomic molecule. That will have some minimum here. That is what we want to find. And from one calculation, we get out one number, this total energy. Doesn't tell us anything, but eventually we can calculate the derivative of this total energy with respect to this position, and that is the slope of this curve. And when we get the slope of this curve, we know if we should move the other atom to the right, or if we are here, to the left. Now, in one dimension, that's trivial. We could just do a second calculation and would know if the energy goes up or down. But think of 100 atoms, 3 coordinates. We have 300 degrees of freedom. So actually, we need these forces to optimize all these 100 atoms. Otherwise, no way to do this. The calculation of the forces has this famous Hellman-Feynman force contribution, which coming from the electrostatic potential. The first derivative of this term gives us the electrostatic potential, gives us the Hellman-Feynman force, but because of basis set incomplete basis set corrections, we also have to do some corrections. Never mind the details of this. Oops, always wrong. So this is the loop we have to do. We start with some atomic positions, get the first density, first potential, solve the eigenvectors, get a new density, mix it. If it's converged, we do this SCF loop. And once this is converged, this inner loop, we would optimize the atomic positions and change the atomic position. We have also in Wien a new approach, and that is we optimize the position and the charge density at the same time. I will indicate this in a second using, for instance, this picture. So this is a two-dimensional energy surface, which we don't know a priori, of course. We want to find this point, and we started somewhere at some x and some y. Let's say we started here. We get one total energy, but fortunately also a force. The direction of the force, x, y, if it's two-dimensional, and some magnitude. Of course, from this alone, we have no idea how far we should move the atoms. We only know we should go in this direction. But whether we should go here or here or here, we have no idea because we don't know these contours, right? So we go somewhere, and then the force, make the second calculation. The force, again, is the derivative of this energy. So it goes up maybe, and if I move it too far, I go like this, and I may go oscillating. If I'm clever, then after some steps, I find my minimum. Now, each point is a full SCF cycle with 20, 30, 40 SCF iterations. Now you can ask yourself, why do I need the exact forces here? It's useless. I don't need to know that the forces here are in x direction 14.7835 with whatever accuracy. It's completely useless. Let's calculate this force only approximately. That means let's do just one SCF cycle. Hopefully we get a force which points somewhere in this direction at least, and let's move the atom a little bit in this direction. So instead of doing 40 SCF cycles here, then moving here, 40 SCF cycles here, moving here, 40 SCF cycles here, we do one SCF cycle, moving, let's say, here, one SCF cycle, moving maybe here, one SCF cycle, moving here, one SCF cycle, tuck, 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 and are coming over here. Okay? So this is a more efficient scheme which is also implemented. So what does it? If I have a problem like this, there is bismuth, and there was an impurity, a tungsten impurity in this bismuth over here. Okay? Tungsten has a different size than bismuth. Bismuth atoms are fat and thick. So there will be a relaxation of these bismuth atoms around the tungstens. They will come closer or move away or whatever.
And talking about these SCF cycles and making it efficient just by doing one, will it also be possible, for example, if I start, from my starting point, I just do a density-based Hamas-Fermi kind of calculation. And then once I approach kind of equilibrium point, then I turn on my own championing. That may also make it quite efficient.
Might be, yes, yes. What we are doing usually is a different trick. That is, when we have no idea about where we are, we do a very lousy calculation. That means we use for this calculation very, very little K-point mesh and a very, very small plane wave cutoff. I talked about 50 to 100 per atom. Now maybe I'm using only 25. That makes my calculation immediately 10 times faster. Because as you have also indicated, it's not interested in this optimization whether the force is really of that size, let's say, in this direction at that point. Any result which goes in this way is fine, and I want to make it as fast as possible. Maybe that would also work, I don't know.
Why don't we just take a sign of the force? That means you know that it's negative or positive, you don't care about the magnitude.
Yeah, but how much should I move it?
So anyway, you are not concerned about the magnitude.
Yeah,
So you know it's negative, then you move in this direction.
yeah, that's what we do. Yeah, 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 yeah.
And what if you are trapped in a local minimum?
Okay, that's bad luck. Okay, so if a potential energy surface does not look like this, but has a local minimum somewhere, either in one dimension, you can plot it easily. It may look like this, and it's obvious. So this is my coordinate x, which I want to optimize, and this is the energy in one dimension now. If I'm starting here, then I'm going down, and I probably will end up here.
And in the non-collinear case, it's highly likely that you will have multiple ground states, like crystal states.
Okay, I would say in crystals, it's not such a big problem. Okay, in real crystalline materials. In molecules, for instance, that's a mess. In amorphous systems, it's a complete mess, even worse. In clusters or so, there are many, many different possible geometries which are all metastable. In solids, that happens not so often. It doesn't mean that it may not happen. It can still happen. There is no way out except try it. Who says that I started here? So I'm starting here and I find some minimum. So then I do another calculation and I'm starting over here. And if this gives me the same minimum, I might have some idea, maybe, and then I'm starting here. And if everything goes to the same minimum, I'm happy. Okay, still no guarantee, because maybe I was starting from here, and one calculation I was starting from here and one from here, and they all converge to this. Bad luck. Yeah? So you have to be clever in choosing your initial states. There are ways out of this in certain cases. So one way would be you could do finite temperature molecular dynamics. That means you calculate the forces, can do also with Wien, and then follow the forces, and if the atoms are coming too close, the force will change sign and they will go back and forth. And you give it a certain temperature so that the average velocity is this temperature. And that means then the atoms will move in this potential over here and eventually get trapped. So I go high temperature, they will move, and then I lower the temperature, and if I'm happy, then it overcomes this barrier and finds this way. If I quench too fast, bad luck, I'm still ending up here. If I quench too slow, it takes ages until it comes here. Whatever, no guarantee, but one method. There are also other methods. Parinello or so has found a clever scheme. Schematically, he found the first minimum here. Okay? So what he does is, around this minimum, I'm adding a potential. Okay? So now let's do again. I'm here, going somewhere. Found another minimum. I'm adding another potential. And I'm here. Okay? Can work. No guarantee that it works. Okay? There are all sometimes two potentials. I mean, if it's like this, it will work. But there is no guarantee that the potential surface does not look like this. Okay? So that means this is almost infinity or whatever. Then you can fill whatever you want. Your atoms will dissociate first or something like this, and you will not come from here to here. Yeah? So unsolved problem, I would say, in general. In practice, people are working as good as they can. Okay, so what we want to do here is optimize the position of these bismuth around these things. So if we proceed, we find a large total energy, a high one, and we have some forces, big forces on some atoms, okay? So we move the atoms, the positions, along these forces in certain directions. The total energy must drop, variational principle again. The lowest energy, this state here must have the lowest energy, of course. The total energy is dropping, sometimes with whatever, because we are overshooting or so. You see forces may oscillate or whatever. At the end, the forces are zero, and we have found the relaxed structure. And this can really have a severe impact on certain properties. The question here was, they have measured the electric field gradient on the bismuth here. Atom with this tungsten impurity was minus 4.6 or well, plus 4.6 in these units. That can be measured by nuclear quadrupole resonance. And if you start in the starting geometry, you get out, I don't know, 0.5. So the calculation does not agree at all with experiment. So after you do your structural optimization, you end up with a field gradient which has this value of 4 or something like this in reasonable agreement with experiment. Okay, now let me finish with a summary of a couple of properties which you can calculate. Of course, Wien is a band structure method, so we can calculate these band structures. And there was some questions, what is the meaning of these eigenvalues? And we said, strictly speaking, only the Fermi level. The states here have any meaning, and Fermi level is connected with the Fermi surface. So let's compare here first this plot. This is vanadium selenium 2, for instance. There is a Fermi surface measured by which technique? What do you guess? angle-resolved photoemission spectroscopy. You can measure the Fermi surface, and you see that matches, the lines here is the theory, that matches perfectly, you can say, in such a case. Not always the case, if we have bad luck, not, but here it really matches perfectly. Here we are even more lucky. They have measured not only the Fermi surface, so that at energy 0, but also the dispersion, the band structure, if you want, up to 6 electron volts. And you can compare now the band dispersion with the calculations, and you find, I would say, a pretty good agreement between theory and experiment, even, or although these bands, these eigenvalues, have strictly speaking no meaning. So you would have to do formally, for instance, a GW calculation, doing these quasi-particle energies, and then you could justify to compare theoretically the bands with the experiment. In practice, in a material like this, it works perfectly and pretty good, let's say. If you look in some fine details, you may find there are some discrepancy. There is some intensity, so this one band should not go up all the way, but should probably go down here already. And maybe here you see that the bandwidth is a little bit too narrow, should be a little bit further. But this is less than tenths of EV or so. Perfect. You can even do this for very complicated systems. Hexagonal boron nitride, a monolayer of this boron nitride deposited on a nickel 111 surface. When you measure angular resolved photoemission, you clearly see near the Fermi energy some dispersed bands, some bands. These are the nickel D bands. You cannot resolve them clearly. But you see here down, 2 bands going down and 1 band going up from gamma to K. So just look from gamma to K, and you find 2 bands going down, 1 band going up here. And that can be identified as boron nitride bands. And since angular resolved photoemission is very surface sensitive, you see mainly the boron nitride bands and not so much about the nickel bands. Only where there is this high intensity of bands, you see something here, but you see the surface bands much more clearly than the underlying nickel bands. So in favorable cases, works very nicely. In the exercises in the afternoon, we will have a case, strontium vanadate, where there are severe problems. You can calculate, of course, densities, potential, X-ray structure factors, spin and orbital magnetic moments. You can also calculate only partial electron densities. For instance, a density of states like this, of an niobate, and there was a funny peak of this, and you want to analyze what is the character of the wave functions, or the charge density of this peak. You put in this energy window, and you calculate then such a charge density, and there is a tetrahedra of niobium atoms, and there is a dz square orbital pointing in the center of this tetrahedra.
There is of course a matrix element of the dipolar A dot P interaction, and is that currently implemented in WIEN2k?
No.
Is there a plan to have somebody doing this? That would be very useful.
Would be very useful, yeah. We were once thinking about it. Would be interesting.
We should talk about it.
Yeah,
maybe.
yeah. Would be very much interested. Because you see in this photoemission, there are some interesting features. If you go along the Brillouin zone, in principle here is gamma, so the right side and the left side, they should be completely symmetric, clearly, in terms of energy. No way out. But in terms of intensity, it is sometimes not. You see it's strong here and very, very weak here. And this has matrix elements effects, depending in which part of the Brillouin zone you are, in which reciprocal unit cell or so you are. An example where you really need an all-electron code, not a pseudo-potential code, basically, is when you want to calculate hyperfine parameters. That means quantities coming from electrons, of course, but measured at the nucleus, measured at the position of the nucleus. So NMR, Mössbauer spectroscopy. So hyperfine field, Mössbauer isomer shifts, NMR chemical shifts, or this quadrupole splitting, or I call it here electric field gradients. And this is an example of aluminum NMR spectroscopy. And look, for instance, here, never mind the details, the open symbols of these 16 different compounds, the calculated value versus experiment. And if you look at the open symbols, they are all over the place. There is hardly any correlation. Why is that? Because we use the experimental geometry. And for some of these materials, the experimental geometry is apparently very, very wrong. Okay? It's easy to determine lattice parameters with X-rays, but the position of the atoms is much, much more difficult to find. If we do a structure optimization, we got the full symbols. And you can see the full symbols within the error bar of experiment are all in this 45-degree line and fits perfectly with experiment. Of course, we have a total energy. I talked about this. We can do forces structure optimization. We can also use this to calculate phonons. Phonons can be compared with experiment. Which experiments? Raman. What else? Infrared. Which phonons do you get only with these methods? Only the gamma point phonons. So also phonons have a dispersion like the electrons, have a band structure. What I show you here is a phonon band structure. With infrared you can measure only gamma, and also there are certain selection rules. Not all the phonons can be measured, and so on. Dipole moment and things like this depends on that. How can I measure the phonon dispersion completely? Neutron scattering, exactly. Yeah? Big single crystals are necessary. It's difficult experiment, blah, blah. I don't know the details, but possible. So we did a calculation. That's nice, so you can compare with experiment, but phonons are also useful for a very, very different thing. We did a calculation for a cubic pyrochlore structure of yttrium niobium 207. This is this cubic structure. If you do this, it is metallic. Experimentally, it's an insulator. So maybe some people in this audience would say, d electrons, strongly correlated system. Could be. But before we went to this, since niobium 4D is not really so correlated, we are hoping, we calculated the phonons. And what you saw is we have a lot of branches with imaginary frequencies. And that means this cubic structure is dynamically unstable. What does that mean in terms of a simple picture? If I plot the total energy as function of some coordinate x, could be a displacement of an oxygen atom, I have a situation where the potential looks, maybe like this. I'm sitting here at the cubic structure. It's perfectly stable alone. Force, the derivative, is 0. Nothing happens. But I'm not at the minimum. How do I find that? By doing the phonons. What are phonons? It's the curvature of this curve. Typically, a phonon would have a positive curvature at around the equilibrium. That gives me this phonon here. Here I have a negative curvature. That means my frequency is imaginary, and we found this. And all you do then is you look at the lowest eigenvector, lowest frequency, you freeze in this phonon mode, and you do then a structural optimization, and you end up with a structure which has small and large niobium tetrahedra, while the cubic one is all the same. Okay? Experimentally, it was not found in this powder because, of course, the average of this small and large gives you the cubic structure. The resolution was not good enough, and that gives you an insulator. That's it.
So you cancel the Coulomb frequency only at high symmetry points?
Everywhere.
But the supercell calculation?
Yes, but
Gamma n is interpolated or?
it's interpolated. It's using this and gets the force constants. So you do a supercell, but then you get the force constants, and if the force constants are falling up to 0 at some point, and with this you can then calculate the phonons at every Q point. Yeah. Okay, you can do spectroscopy, and again, in principle, that's not valid. Spectroscopy is always excited state properties. But you can do a lot with this. For instance, you can do XPS core level shifts. For this, we use half core holes in Slater's transition state. I don't know. Yeah, can I explain this? Then might be interesting because it has also a connection to what you have seen yesterday. Yesterday, it was shown that the total energy as function of occupation number, n minus 1, n minus 2, was changing, right? And it should change something like this, right? That was a picture we saw yesterday also on the blackboard. And, of course, this energy difference from here to here, this would be my excitation energy. That's what I want to measure also for a core electron. So this is the occupation of some core level also. Now, if you do the same plot in GGA, you get out a curve which is not straight lines in between, but it's a smooth curve. It's wrong, it's physically not correct, but that's what it comes out. And then remember on Janek's theorem that the eigenvalue epsilon I was the derivative of the total energy with respect to the occupation of this state, right? So that means the eigenvalue gives me this slope here of this curve. And of course, as you can immediately see, this energy difference from this slope is not enough. Therefore, my energy, my eigenvalue of the core state is not a good approximation. So Slater realized this situation and said, let's make a trick. Let's make half a core hole and calculate the eigenvalue at this position. That is the slope here. And this slope is nearly perfect. Of course, not exact, but it's a very, very good approximation. And it's a very cheap method to calculate core levels in solids. You can do X-ray emission, X-ray emission, absorption, and energy electron loss spectroscopy. And just one plot here. Absorption spectroscopy means you have a photon coming in, which is absorbed. It will excite a core level into the unoccupied conduction band. With dipole selection rule, of course, delta L plus minus 1, so from an s orbital into a p orbital unoccupied. If you do this for magnesium oxide, magnesium K spectrum, this is the experiment, and this is the ground state calculation. Well, we find maybe a 2-peak structure, but the intensity ratio is very bad. Why is this? The ground state is very bad. We have to do what is called a core hole supercell calculation, and then get the spectrum looking like this, and that matches perfectly with the spectrum. The reason for this is explained like here. If this is my ground state, the core levels, the valence band, the conduction band, we want an excitation of this core level into the conduction band. Now, if I have now a hole here, it is fairly clear that the conduction electrons can be stronger attracted by the nucleus. The nucleus is less shielded by the core electrons. That means these states will come down, will shift down from here maybe to here. And actual transition is governed by the so-called final state rule, will be the energy from this level to the relaxed state. And that we simulate with a core hole. That works, again, very, very well for K-edges, X-ray absorption, the edge structures very well. Not for L-edges so good, because here we need a much, much more sophisticated treatment. It's called the BS-beta-Salpeter equation, solving basically a two-particle Schrödinger-like equation with some approximation. I don't talk about these excitonic effects. There is no time. Just let me finish with some other properties. Transport, Boltzmann transport can be done. Alloy theoretically automatic toolkit, that means cluster expansion. You can do these periphases, which we heard this morning and yesterday, also with WIEN. There is a module Berry PI, and there is also a GW code. In principle, you should have this quasi-particle, who somebody was but the quasi-particle energy in GW is calculated from the LDA bands, and then taking the difference between this orbital-dependent self-energy and the LDA potential. Now, if I'm lucky and this difference is almost zero, then my energy bands are in good agreement with theory. No guarantee that that happens. We have many examples where this is a very, very clear term and important term, but in particular for metals, it is not such a bad approach. And furthermore, sometimes this is just a constant, so you get these rigid shifts. People are using what is called the scissors operator for a semiconductor. They cut away the main structure and shift it, the unoccupied states, up by some constant, and this is as a first approximation also possible. Okay, in summary, I hope DFT can give you insight, can help you to interpret your data, and can narrow maybe the design space if you want to find some new material. DFT usually cannot really tell you do this and this, because after all we have lots of approximations, but it can give you some hints. And with this I acknowledge in particular my two postdocs, long-term postdocs, Fabienne Tran and Robert Laskowski, and Professor Karl-Heinz Schwarz, who is retired since 7 years and still comes every day more or less into the lab, still active, and I thank you for the attention. Any questions directly to this?
Why you need supercell, not unit cell?
For
phonon calculation, why you need supercell, not unit cell?
What you want is, again, think what means, I have to draw it like this, what means K space, K points. If I have an atom here in this cell, and I have gamma, means that if I displace this atom here, I will also displace it over here. Okay? But not every phonon will do this. There could be phonons where not all atoms are moving in the periodic image in the same way, but they could be, for instance, moving oppositely. If this is moving right, this could move left. And this I can only describe by a supercell. Okay?
How much is the size of supercell?
We calculate then the so-called force constants. That means if I have in my atom, in my unit cell, certain atoms, I displace one atom, and I get the spring constant, the spring between, I have to draw it like this, what means K space, K points. If I have an atom here in this cell, and I have gamma, means that if I displace this atom here, I will also displace it over here. Okay? But not every phonon will do this. There could be phonons where not all atoms are moving in the periodic image in the same way, but they could be, for instance, moving oppositely. If this is moving right, this could move left. And this I can only describe by a supercell. Okay?
How much is the size of supercell?
We calculate then the so-called force constants. That means if I have in my atom, in my unit cell, certain atoms, I displace one atom, and I get the spring constant, the spring between these atoms. But of course, since my unit cell is so small, I also displace this atom, okay? And therefore I get also a spring to the next unit cells. And that I don't want, because I only know the total spring, okay? Not the individual components. So if I use a larger unit cell, this is not displaced, so there is nothing which is displacing here. And only here, this atom is also displaced. But if this is big enough, I can safely ignore this spring here. That is basically 0 because it's so far away. So how large the unit cell, supercell, depends on the system and the accuracy you want to have. Yeah? Typically, 64 atoms is okay. 64 to 100 atom supercells is usually okay.
Calculation for this with this core hole, you are trying to simulate all that. So there will be a very strong correlation effect between this core hole and this valence electron. So is that taken into account by doing just simple LDA plus U calculation, or how is it?
This was magnesium oxide. There's no LDA plus U at all.
Mm-hmm.
It's only necessary that you have in the oxygen, or this is magnesium K. The
KH.
KH, the
KH.
one S electron of
Yeah.
magnesium is missing,
Yeah.
and that is important only in one atom
Yeah.
of a supercell. Again, think of an experiment. We are exciting only one atom out of 10 to the 23 or so, or very few atoms. Not every atom in the unit cell, of course, in every unit cell.
So you single out this core. I understand that. but
So
then-
that allows them to relax, it's just a Coulomb effect, to
Yes.
relax the other electrons and get stronger attracted. They shift down in energy.
But that relaxation will depend on the correlation effect between this one and the rest.
Sure.
So that's exactly was my question.
Yeah.
Was GGA enough to sort of capture
Here,
this?
it's fully enough. I can even show you, if you want, this for an L-edge or so. This is calcium fluoride and L-edge. This is experiment. If you use a ground state DOS, it looks like this. It has nothing to do with experiment, you could say, right? If you do a core state, core hole calculation, you already get this localization. So from the ground state calculation with a core hole calculation, I get this doublet and nothing here and here anymore. But since P1/2 and 3/2 are independently, I get, of course, an intensity ratio of 2 to 1, since I have 2 core electrons and 1 electron. But the experiment is 1 to 1. Must be some reason. And for this, you need now really BSE, fully relativistic Bethe-Salpeter equation to solve this. This equation, maybe has a Coulomb, a statically screened Coulomb interaction between the electron and the hole, screened with the dielectric frequency, Q-dependent dielectric constant, but it also has an exchange contribution. And this exchange contribution is, of course, missing in principle with the core hole calculation. And you can even simulate this. If I do a BSE independent of L2 and L3, I get this ratio of 2 to 1, similar as here, and not in agreement with experiment. And I can, even further out, I can remove the Coulomb term, then I get this delocalization, the same as the ground state. And if I remove the exchange term, I still have my localization, but I have this 2 to 1 intensity again, which is not agreeing. So I need the full thing to get it. And we can, this is cross terms which you can explain in
And that's
here.
implemented within the code. That's implemented.
That's implemented. It's an add-on, and I must say these BSE calculations are really expensive. So if you don't have 200 or 500 cores with a couple of 100 gigabytes, you don't even need to try it out. Okay.
So any other questions? So if
Yeah.
The amount of hole. Amount of hole created. How much depend on that?
For core hole spectroscopy, it depends on that, yes. It's also not always, if you really want to have agreement with experiment, clear that one core hole is the best agreement with experiment. From the theoretical point of view, you should probably have one core hole in an as large as big supercell, because the other atoms can then contribute to the screening of this hole. If your supercell is too small, only this one atom where the hole is, that must react completely and gives you a too strong downward shift. If there are other atoms around which have no hole, they can contribute to the screening, and all the electrons can shift down a little bit more. And if your supercell is not big enough, you can mimic this by making a little bit smaller core hole. Okay? We will have the exercises in the afternoon and also tomorrow, so we have lots of time for discussions, for further questions. You can just ask any time, of course, you want. Yeah?
If not, let's thank the speaker once again.